This is 3D printed lunar soil simulant. NASA is planning on establishing a permanent lunar colony on the south pole of the moon. This would allow humanity to take its first foothold amongst the stars in an effort to become multiplanetary. It's extremely expensive to send mass to low Earth orbit, not to mention all the way to the moon. This facilitates the need for something called in situ resource utilization, which is essentially just taking the material that's already on the moon, like the lunar soil, and using it to build the infrastructure needed to build a lunar base. Things like roads, launching and landing pads, and of course habitats. Here at Florida International University, we are researching methods to use the lunar soil simulant sent to us by NASA to 3D print bricks, parts, filters, and other structures that could be used to build a lunar colony. We used a digital light processing or DLP 3D printer. The way it works is a viscous slurry is poured into a vat. Then a UV light source cures the photocurable ceramic loaded slurry onto a print bed. The photoinitiators convert the light energy from the UV light source to chemical energy. The photoinitiators cause a chain reaction that causes the monomers and oligomers to cross-link. Monomers are simply single molecules. When they are single molecules, they could flow over each other and the slurry is in a liquid state. When the monomers link up and polymerize, the slurry cures and hardens. Our partners at the NASA Marshall Space Flight Center in Huntsville, Alabama, graciously sent us a lunar soil simulant. The scientific term for lunar soil is lunar regolith. This lunar regolith simulant simulates the regolith from the south pole of the moon, in the Highlands region, and it's called Greenland. The Greenland regolith is made up of mostly alumina and silica. It has an average particle diameter of approximately 8 microns plus or minus 7 microns. The regolith has to be mixed with a photocurable resin in a concentration that allows for good flowability. At 70% regolith and only 30% resin, the slurry shows poor flowability. At 60% regolith and 40% resin, the slurry shows excellent flowability. Flowability is important during printing. The heat from blending or from the heater in the printer reduces the viscosity of the slurry. The 3D part is sliced into 2D layers, and the image of that 2D layer is projected with UV light. This cures a specific part of the slurry into a desired geometry and onto the printing bed. The printing bed then rises, the slurry flows back and evenly fills the vat again. Then the print bed comes back into the slurry to cure the next layer onto the part. This is why flowability is so important. If the slurry doesn't flow back, then there's simply nothing to cure onto the print bed. After the print is scraped off the print bed, it is cleaned with IPA and the part is placed in a chamber with a spinning table and UV light. It's placed in this chamber for the same amount of time that it took to print the part. This cures any resin that remains in the crevices of the part. We printed complex and intricate pieces to test the viability of this technology. This calibration print allows us to see how well the material prints, and it shows if any parameters need to be adjusted. That's really the hardest part of printing a ceramic part. Dialing in the right parameters is quite challenging. For example, this is what happens if the slurry is too cold. The left piece was printed at 20 degrees Celsius and the right piece was printed at 25 degrees Celsius. The reason for the deformed part is that since the slurry was too cold, it was too viscous. This caused the layers to be infiltrated with air gaps. If there's air gaps everywhere, there's no material and nothing will cure in that area. This will cause the finished piece to have slightly deformed areas. The next step is to sinter the part in an ambient air box furnace. This makes the part 21 times harder. During this process, the resin is removed and the particles are fused together. It does not melt. What happens is a solid mass transfer. Due to the law of thermodynamics, the particles want to reduce their surface area energy. They achieve this by merging into each other. The final sintered piece is 5 times harder than mild steel, and it goes back to the color of the regolith because all the resin has been removed. The piece on the left was printed at 20 degrees Celsius and sintered, and the piece on the right was printed at 25 degrees Celsius and also sintered. This is an animation created using actual scanning electron microscope images. You can see that the resin is vaporized and the particles fuse together. The removal of the resin does leave some porosity in the part, and the goal is to reduce the porosity as much as possible by loading the slurry with regolith at as high of a concentration as possible. There's shrinkage of around 6% in the X and Y direction, and gravity causes the part to shrink 14% in the Z direction. We also printed samples for thermal testing. The sintered sample cools quicker than the printed non-sintered sample. And the sintered sample also heats up quicker than the printed non-sintered sample. We also ran an experiment for the coefficient of thermal expansion. This shows how much the material expands when it's exposed to heat. The CTE of concrete on Earth is 10 times 10 to the negative 6. The temperature range on the moon is negative 255 to around 165 degrees Celsius. The CTE of the sintered regolith at this temperature range is around 3 times 10 to the negative 6. This shows that the sintered material is thermally stable enough to be used as a construction material on the moon. We also ran something called thermal gravimetric analysis, or TGA. Basically, this shows how much weight is lost in the sample in relation to temperature. So it goes from 0 to 1,000 degrees Celsius. You can see that the sintered sample loses no weight, while the printed sample loses 40% of its weight because 40% of its weight was resin. So it proves that all the resin has been removed. We also created a 3D model of the complex cube calibration print layer by layer. This was really cool because it allowed us to create simulations based on the material. These simulations perfectly matched the experimental compression testing. What's cool about the simulations is that you can actually see what's happening in each individual layer. You could even see what's happening between 2 layers or 3 layers or whatever you want to see. This is valuable information when designing parts and structures this way for the moon. We also created a small-scale lunar habitat that astronauts will one day call home. There's still a lot of work to do. However, I think the most important thing about this research project was the characterization of the thermal and mechanical properties of the 3D printed and sintered regolith pieces. Whether it's printed with DLP, digital light processing, or printed with ink writing, or whether it's casted, this project has shown promising viability for the 3D printing of regolith for use on a lunar base. As we colonize the moon, we will then colonize Mars, and humanity will eventually become a spacefaring civilization. And one day, we might see ads for vacations to Earth on alien worlds. If you'd like to learn more about this research, feel free to read the full research paper. The link is in the description. Thank you so much for watching and have a great day.